In this section, we'll talk more about conditional probability and how that ties into independence. So remember how we defined independence? We said that two events are independent if they don't affect each other. That means we could also say that two events are independent if knowing that one occurs does not change the probability that the other occurs. So this means that the probability of A given B is equal to the probability of A. This is saying, well, even if you know that B happened, that doesn't change the probability of A. So probability of A, if you know that B happened, is still just the probability of A because B does not affect A. And that leads us to our formal definition of if two events A and B are independent. This is how we prove whether or not they're independent. Is we look at a conditional probability. So we compare the probability of A given B to the probability of A. So if the probability of A, if you know that B happened, is still just the overall probability of A, you know that B didn't affect A. So they're independent. So let's try some examples. Let's consider drawing one card from a 52 card deck. First, what's the probability that the card is a jack? So the probability of a jack, well, there are 4 jacks out of 52 cards. So we have 4 out of 52. I don't normally bother simplifying, but I will in this situation so we can compare our final answers. Okay, part 2. If I draw a card from a standard 52 card deck and I tell you it's red, what's the probability that it's a jack? There are 2 ways you can do this. You can use just logic, which says there are 2 red jacks out of 26 red cards, since we know it's red. So the probability that it's a jack, if you know it's red. So again, there are 2 jacks out of 26 red cards. Notice this simplifies to 1 out of 13. Okay, which we'll talk about in a second. But now let's look at our actual formula. How would you do this with the formula? So the probability of a jack given red, if we want to use the formula, is you do the probability of the intersection, or the AND, so jack and red, over the probability of red. Well, how many jack and red cards are there out of your entire deck? There are 2 that are jacks and red out of your entire deck is out of 52. And probability of red, there are 26 cards out of an entire deck of 52. Now you might notice here, we have over 52 and over 52, those cancel and we just get 2 out of 26. So when we use the logic, it was kind of just a shortcut, but we get to the same answer of 1 out of 13. Okay, so you might notice that the probability of jack, if you know it's a red card, is 1 out of 13. But the overall probability of a jack is still 1 out of 13. So this means that the overall probability of getting a jack is 1 out of 13. But we know, if we know the card's red, the probability of getting a jack is still 1 out of 13. So that means whether or not you get a jack does not depend on whether or not the card is red. The probability of getting jack doesn't change at all if you know the card is red. That means that the card is red and the card is a jack are independent events. Okay, so there's another one for you to try. This one looks at the summary of gender and types of jobs at a university. You can see that we have males and females, and then we have 3 different types of jobs. Let's find some probabilities. The first one is that find the probability of randomly select a person is male. So probability of male, let's see, there are 200 males out of a total of 300 people, which is 0.666. Let's see, I like to do 4 decimals if we're talking about probability. See, probability that I randomly select a person is faculty. So probability of faculty. Notice I told you the abbreviation C is faculty. There are a total of 120 faculty out of a grand total of 300. So 120 out of 300 is 0.4. A randomly selected person is both faculty and male. So probability of faculty and male. Let's come back up to look at that. So the ones that are faculty and male would be 110 out of, again, our grand total of 300. So 0.366. Let's see, what's the probability that a randomly selected person is faculty if you already know that they're male? So the probability of faculty, if you know they're male. So let's go ahead and use our formula here. If you want to kind of use the shortcut looking at the table, that's fine too. So this will be faculty and male divided by the probability of what you know, which is probability male. So this gives me, you were right. Oh, that means, sorry about that. Okay, so we have the probability faculty and male over probability male. Let's see, and we found all those, which is why I made you find them. So faculty and male is this 0.366. Probability of male is 0.666, which equals 0.555. Now this is interesting because the overall probability of faculty is 0.4. But if you know they're male, the probability that they're faculty suddenly jumps up to 0.55. So that's kind of telling me you're more likely to be faculty if you know that you're male. Let's try 5. A randomly selected person is faculty if you already know that they're female. So probability of faculty if you know that they're female. Actually, I don't remember what I did for that. Oh, female is just F. So this will be the probability of faculty and female over probability of female. So you'll have to scroll back up. Faculty and female is going to be this 10 out of our grand total of 300. And for female, it'll be 100 out of 300. So we have 10 out of 300 and 100 out of 300, which should give me just 0.1. So notice here, the probability of your faculty if you're male is 0.55. The probability of your faculty if you're female is 0.1. This tells me there's something going on at this university. It doesn't seem quite fair. You're much more likely to be faculty if you're male. Let's see, so 6. Are the events male and faculty independent? Give a numerical reason. So this is where we kind of do our proof. So to do this, we would look at a conditional probability. I'm going to do the probability of faculty given male because I calculated that already. And this is equal to 0.555. Now the probability of faculty, the overall probability of faculty is 0.4. Notice these are not equal. So that means your probability of being faculty So your probability of being faculty changes if you are a male. That means they are dependent. They affect each other. So again, because the probability of being faculty changes if you know they're male, they are dependent. And finally, let's just ask ourselves, is a randomly selected employee more likely to be faculty if the employee is male or female? So the probability of faculty given male equals 0.555. The probability of faculty if you know they're female equals 0.1. So you are much more likely to be faculty if you are male, 0.555, versus 0.1 if you know you are female.